In this video we will be looking at page 304, section 4.3, problem number 5. This will be the last section for our test that's upcoming in a couple of weeks. The problem says life expectancy. Life expectancy in the United States has been rising since the 19th century. The table shows the U.S. life expectancy in selected years. It gives the year and the life expectancy in number of years. A says let T represent the number of years after number of years after 1950, and my Y column is going to be life expectancy. Okay, so 1950 becomes 0, and 1950 corresponds with a life expectancy of 68.2. 1960 would thus be 10, and that's 69.7. 1970 would be 20, and that's 70.8. 1980 would be 30, and that's 73.7. 1990 would be 40, that's 75.4, and 2000 would be 50, and that is 77. So as you can see, as the year has increased, life expectancy has increased. We've better medical technology, better many things has led to greater life expectancy. Alright, so we're going to now plot this data. First, why this transformation into making this 1950 0? Well, it's just a matter of form with regards to the graph. Now we can begin, we won't have to begin the x-axis at 1950, we can begin at 0. And it may make the equation a little bit easier to look at. So I only need positive values for x here. So I'm going to draw a first quadrant graph. I don't need all 4 quadrants like in our previous sections. Our x-axis is years after 1950. Alright, our y-axis is life expectancy. Okay. All right. I'm going to make each one of my small lines worth 10. So starting here at 0, this would be 10, 20, 30, 40, 50. Could have went out a little bit further to make this graph a little bit more appealing, but it'll be okay. All right, my vertical axis, I could start here. I can say this is 70. I'm going to indicate a little break in my graph, meaning this first division is different than the rest of them. So my first year here will be 68. Alright, and I'm going to make every 2 lines one more. So 68 and a half, 69. 69 and a half, 70. 70 and a half, 71. 72. 73. 74. 75, 76, and then one more up would be 77. All right, so year 0 pairs with 68.2, 0 pairs with 68.2. And that would be here. 10 with just short of 70. 20 with 70.8. 20 with 70 point, that's 71. That's 70.8 would be right there. 30 with 73.7. 40 with 75.4, 40 with 75.4, and 50 with 77. 50 with 77 would be right here. Okay. And as you can see, although these points don't fall on a perfectly straight line, they look like they're somewhat a linear form. So I'm going to employ a straight edge here, just simply another piece of paper. And I'm not trying to draw a line that hits as many the points as I possibly can. I'm trying to draw a line that sort of averages out these points. And this one looks pretty good to me. Alright, that is my best fit line. Remember, we don't show it extending forever. We only want to consider the values that we have. The model is only used to predict values that we know in our domain, in our set of x values, our set of input values. So this is our best fit line, our trend line. Best fit line. Okay, that's what we call this line here. Now, if we really wanted to get a really good best fit line, we could use some software. And here I've used my calculator to draw the line. And you can see that the line I have here is very similar. The actual best fit line pretty much went through the first and second points and that final point. And here you can see the same. First and second points it hit, and it hit the final point as well. The reason this line is hitting so many of the points is these points are pretty much on a straight line. So if we found the correlation, the R value we talked about in class, that it would be very close to 1. All right. So that is part A. A, find the best fit line. B, find an equation for your regression line. Best fit line, also called the regression line. Okay. So we want to find the equation for this line. The purpose of us going over regression is to see that there is an application for our slope-intercept form and to get additional practice from writing these equations. Well, to find an equation, select 2 points on the line. Not necessarily points that are in our data. Well, fortunately here we have a couple of points that are truly on the line and fit our data. So this very first point appears to be on our line, 0.68.2. 0.68.2. And so does our last point, 50 pairs with 77. Now this was just a coincidence. I'm going to choose this point here. It looks like it's a little bit more on my regression line. If your regression line is a little different than mine, no problem. All right. Again, we would to find a really good regression line, we would use our calculator and find the least squared regression line. 40 pairs with 75.4. Okay. These 2 points are on our line now. We're ready to find the equation of a line. Remember our slope-intercept form. Y equals mx plus b. M is our slope, b is our y-intercept. Let's find the slope. Slope is change in y divide change in x. Well, subtracting our y values, 75.4 minus 68.2. Subtracting our x values, 40 minus 0. 75.4 minus 68.2. That is 7.2. 40 minus 0, that's 40. Dividing 7.2 by 40. That is 0.18. Our slope here is 0.18. Okay, in the context of our problem, remember, slope is change in y divided by change in x. So we are increasing our life expectancy by 0.18 years per year after 1950. 0.18 years, well, that's about a fifth, all right, close to 0.2, okay. So 1/5 of a year is a little bit more than 2 months. So on average, we've been living 2 months longer per year since 1950. That's pretty substantial. Okay. Now we need to find our y-intercept. So we'll use either of these points. It doesn't matter which one, okay, because they both fall on our line. I'm going to use this second point. Back into y equals mx plus b. Instead of y, I will substitute 75.4. We're substituting into y equals mx plus b. Y has become 75.4. Slope we just solved for, it was 0.18. The x that corresponds with that 75.4 is 40. Now we can find b. From this line to this line, we've simply substituted a corresponding x and y in the slope that we just found. Now we can solve for b. 40 times 0.18. That is 7.2. So we have 75.4 equals 77.2 plus b. Solving for b, we'll subtract 7.2 on both sides. 7.2 subtract 7.2 to leave b. 75.4 minus 7.2. That is 68.2. Okay, this is our y-intercept. And you see that indeed that is the y-intercept that we have in our data, all right? And it was our situation here because we actually used that point in the calculation of our slope. So we could have known that without the solving, but I wanted to demonstrate the solving to you. Again, we did not use these points because they were in our data. We used these points because our regression line actually went through those points. So this equation is for the line, not for these points. It was just coincidental that these points were on the line. So finally we have this equation. Y equals, slope was 0.18 times x plus 68.2. Where this x and y, x is number of years after 1950, and the y is our predicted life expectancy. Okay. C part. Estimate the life expectancy of someone born in 1987. All right, we're going to use this equation. Y equals 0.18x plus 68.2. We want to know if somebody was born in 1987, life expectancy and this is our Y for someone born in 1987. Okay, first, 1987 corresponds to an X value of 37 because we said that our X was the number of years after 1950. 1987 minus 1950 is X value of 37. So our question simply is, if X is 37, then what is the value of Y? All right, we will substitute into our equation. Y equals 0.18. Instead of X, we want 37 plus 68.2. Okay. Multiplying 0.187 times 37. 0.18 times 37. That's 6.66 plus 68.2 is 74.86. Alright, so we're predicting a little bit less than 75. The life expectancy for a person born in 1987 is 74.86 years. Okay, this is a predicted value. Obviously, we're not suggesting that everyone is going to fall over dead. Everybody that was born in 1987 will fall over dead at 74.86 years. Some will be less and some will be more. This is our predicted, our average life expectancy. Okay, so we see that the life expectancy here is a little bit short of 75 using our equation. Now I want to go back and look at the graph and see if we get the same thing. The equation is simply the regression line, so the regression line we should be able to use in a similar fashion. I want to see does 37 pair with about 45. So here we go. Using my line, I'm going to an X value of 37. Here's 30, here's 35, here's 40. So 37 would be right here in the middle of these two. I go up until I hit my line. 30, 40, 37, right there. And you see it would fall just short of 75. So we can use the line, the regression line, in a similar fashion as we used the regression equation in this case. This equation is simply an algebraic way to express this line. Okay. That was question C. All right. Question D says, predict the life expectancy for someone born in 2010. Predict life expectancy for someone born in 2010. Alright, same process. We're going to convert 2010 to some X value. It's an X value that is equal to 60. 2010 minus 1000 minus 1950 is 60. So when X is 60, what is our Y value? Again, Y equals 0.18 times 60 plus 68.2. Okay, this is 79. Okay. Now, one caution here, this is extrapolation, all right? So, while it's not much of an extrapolation, our data is until the year 2000. It's reasonable to assume that our model might be good for another 10 years. We clearly wouldn't want to do this forever because this is a linear situation. If we kept looking on and on into the future, we would say that eventually life expectancy would be infinite, and we know that's certainly not going to be the case. At some point, we could expect a leveling off. In fact, in recent years, life expectancy has even dipped a little bit because of problems with obesity. But bottom line, this 79 is, our model was not made for this. Okay, so extrapolation. Extrapolation is using the regression model for x values beyond our domain. Okay, we should do this with caution. Use with caution. Okay, we do not know how our model would behave beyond the year 2000. So when we say that 2010 would pair with 79, we should be a little bit skeptical of that due to extrapolation. All right, with that, you should be able to complete this assignment.